I mean, just we can stand and just. Yeah. I'll say that. Yeah. Okay. I'm great about that. But I don't think everywhere. That's like there was something in star formation that's not there. But yeah, this is the yes. After we're here. There was nice. Okay. Yeah.
So
Do we want the table?
4 hours.
We do.
We stand for 45 minutes?
I'm not standing for 45 minutes.
I'm not standing for 45 minutes.
We can get up from the table and gesticulate wildly. I know. Did we? Do you want to say something? Yeah. Yep. We're gonna do. People aren't active enough. We're gonna go chase them down. That's my because I don't want to sit facing the lights. Well, the chairs are on wheels. Yeah. We would literally just have some sort of like so.
I believe we owe.
Oh, we're making sure it's good. Next meeting.
Oh my God, that would be.
That would be down. We will do that for a second. It's sort of like things of like kids who sell popcorn, like first 10 things for waste and then in the back. They use it for minor leaguers out and like balls for money for dinner and stuff. It just hatched. Yes.
Can folks in the room hear me when I speak?
Yep.
Awesome.
Jen, can you hear us?
I can, yes. I can't see anybody, but I can hear you.
Okay.
No, they can switch it.
Thank you for joining from the other side of the planet, Jen.
Hello from Portugal.
Take a star. Surprise round.
We're very good. Actually, we decided to switch. We're going to do the exoplanet. That would be a lot of fun.
How much did you learn? That would be good. You just do whatever. So this session comes from here.
We really shot it.
So there's a slide in random education. Actually, what we should do.
I love the idea. People can just pop up. You have like one person generating songs and one person talking, and just like moving through it. Like what you're talking about. I think that would be.
That's what we should do.
I feel very strong, but I don't talk to almost anyone. What?
Boy, it's
We're just starting.
I didn't maybe call too solid. You should see Oxy's some really nice. One day, my way over the template that on this end. Going good.
There's the one.
Good stuff.
Explaining that's vital.
Learned that the groups was sort of yeah. I don't know where we gotta hold on. Is there a way to make the big? Yes. Okay. Like pin hers out. Once we get going. Welcome back, everybody. You pass it around whatever you want. Okay, we're definitely in the home stretch of the meeting here.
Do I need to sit away from you two? I'll sit over here. The two large human beings versus the small human being. Oh yeah, there's views on that as well.
Yeah. Okay, let's get started on this morning's discussion. What's going on here is that the SOC had a number of submissions, contributed abstracts, which all struck the theme of community preparation, whether it was technical preparation or programmatic preparation or target lists or something like that. And we thought it would be a great way to involve a larger set of presenters and participants to try to merge these into single threads and then also stimulate discussion. So we charged two different groups with taking charge of those discussions. Today we're going to do that in sequence. We're going to have a basically exoplanets focused panel, which is David, Eric, Avi, and Jennifer, who's on the big screen. She's actually more than life size. So, and then we'll have a more sort of, everything else in astrophysics focused discussion after this. But the idea here is that after this group shows what the material they have, that we're really hoping for some robust discussion and interactivity with the audience. So I'm going to get out of your way and hand it over to them.
All right, I'll just start. All right, Jen, can you talk so we can all make sure we hear you?
Yeah, do I come through okay?
Okay. Yep.
Yeah, great.
Okay.
Wonderful.
All right, so I guess I'm talking to the front So we're clearly well organized on this. All right, so we spent some time over the last couple of days trying to put just a few slides together to sort of seed the discussion. So there's like 4 or 5 slides. It is probably not a fully comprehensive of the topics that we want to talk about, but that's the whole point of the panel. So Jennifer Burt, who's on the screen in Portugal, Avi Mendel, who's at Goddard, Eric Mamajak, who's at JPL, and me, David Chardy, who's at the Exoplanet Science Institute at Caltech. And so we're going to just sort of flip through these slides. So the first one, Eric's going to talk to this slide to start with.
Yeah, I'll just say we had initially, when we were comparing slides for this, we realized we were kind of going into detail on our favorite subjects, and I think we decided to back this up and really motivate discussion and broaden it. So we're stepping back a bit. I mean, first off, we want to talk a little bit about what do we actually need here in the short term. We've been hearing this term precursor science, and we just wanted to mention this. We saw the results of the first precursor science call just came out, and congrats to the 9 teams that PI'd successful proposals through that, and thank you for people participating in the community workshops last year that led to that. So we were talking about precursor science as these science investigations that inform future mission architecture, ideally by reducing design and/or development risk. What's the science we really want to get done in the next few years to inform the design of HWO and try to identify things that need more work. And then longer term, we'll be thinking about preparatory science over the next couple decades or 12 years, Jason. What's the science that's going to inform early operations and or interpretation of data, longer term projects. And then we'll think about follow-up science later on. And you've seen through different mission cycles from development through maturity, different flavors of this science. So it really boils down to what do we need to know, to what precision do we need to know it, and when do we need to know it, thinking ahead in terms of what science to propose for. Next slide.
So the only thing I would add to that is that on the when do we need to know it, as we have these discussions, actually really think about that, right? There are things that we need to start to know now because they affect what we want to build. There's lots of stuff that we want to know as we build the mission, and this is a theme that we want to talk about. And so keep those separate, try to keep those things separate in your brain, because some things are super important that we have to do yesterday, and some things aren't. And you'll see this theme as Eric and Avi go through their slides.
Yeah, and my last comment is this point about precision. So, and it really feeds into this slide right here, connecting the dots from science questions to observatory requirements. So we had several great talks about how you do a design reference mission or a science traceability matrix, which are technical terms within NASA that really sort of flesh out this exact box or set of boxes, going from a big science question, that is the whole motivation for why you are sitting in this room, to an actual numerical requirement on your observatory or instrument functionality, right? And of course, that can often feel more like this cartoon on the right than it can an actual step-by-step flow. But Aki and others this week laid out the fact that there is a path to do this, and you really need a set of steps that I've pointed out here in bullet points. You need to start from your big question, the physical environment and predictions for your big question. If you say galaxies evolve from Z of 6 at a certain size scale to Z of 2, you need to be able to actually produce a simulation or some other type of hypothesis for what this would be. And then you need to actually predict the signal for the observation you would do. And finally, feed in from that signal to an actual set of mission requirements for the mission or the wavelength band or other factors that you're talking about. And so the reason I've laid it out kind of in gory detail is this bottom point. It really requires collaboration across different science and instrument expertise. The person who may be doing your galaxy simulation work, as we saw from some of the great slides, is not necessarily the person doing observational simulations or thinking about data analysis and the requirements for the mission. And so part of this discussion, part of what we can do here is start building these bridges between the different needs and helping to fill out together as a community this gap that I put here. So, next slide.
Is this me?
This is you.
This is me? Okay. All right. So the decadal tasked the community in building HWO basically with detecting and characterizing the 25 exo-Earths. And so it's this 25 exo-Earths, which is really just, this is a must, right? This is a driving must requirement. That's the whole point of that particular recommendation from the decadal. But there's a huge number of other potential exoplanet wants that we want to do. We've heard this entire week about all these different kinds of science goals that we want to achieve, both exoplanets and non-exoplanets. And so those, from an exoplanet point of view, also need to get to be articulated. And so the precursor science investigations are intended to, influence the design of the mission so that we minimize the risk in obtaining that must, but we also optimize the science output in achieving that goal as well as the other science that we're interested in wanting to do. And so we've already sort of driven towards a series of science gaps that need to be filled. Hence the precursor call that was just the awards that were just announced. But that came from an original Accept Science Gap list, which was more general to exoplanets in general. But then that fed into the precursor science gaps. There were the precursor workshops that took place. I've lost track of your time at this point. Spring or summer of last year. And then this whole thing will continue to evolve as the GoMap and particularly as the START process gets kicked off, both from a science point of view and a technological point of view. And so a lot of what has occurred over the last year and a half, 2 years, has focused on these 25 exo-Earths. But we also, and we need to make sure that we've not missed something, or that, we need to make sure that we've identified the right set of gaps, or think about things that we might not have actually fully articulated. But there's also the set of exoplanet wants. And this also applies to the other science areas as well. And we'll get into that in the next panel as well.
I'll just briefly add. So the Accept Science Gap list, for those that are not in ExoPag familiar with that, this is a document Carl Stapelfeld and I have been produced about 5-6 years ago and have been updating every year. This was looking at particular science areas that are important for informing the design of future specific NASA missions, not just any proposal, but specific NASA missions, and maximizing the science return on current and future missions. So we have a gap list of about 15 areas. I think about 8 or 9 of these were relevant to HWO before we even began the precursor science exercise, and there was a lot of overlap with that. But we get community input on that through the ExoPag every year, and the community participation, obviously, in the precursor science workshops last year. So it'd be great if people stayed involved. If you see something that you think is important, that you think needs to get done to inform mission design specifically, please make sure you're communicating through these ExoPag opportunities to inform the gap list or upcoming workshops. So, Jen, is there anything you want to add?
Yeah, Jen, there are 3 very loud people down here, so make sure you jump in.
I've been on planes for 20 hours, so I'm very happy for you all to walk through the slides for right now. No, you're doing a lovely job of hitting all these overview points. I think it's the right way to start the conversation.
Make sure that if we miss something or say something incorrectly, or you have a different point, please jump in.
I will. I absolutely will.
Okay, right. This is the Neapolitan ice cream slide. So
this is what happens when we work together and we're hungry.
This is also what happens when you don't nearly have enough coffee. All right. So looking at what the gaps that were identified for the exo-Earths, there was, I don't know, 10, 12, something on that order, but they basically fall into sort of three big categories. The chocolate was, really about modeling and exoplanet compositions, and this really feeds into things like the wavelength range that we need and the resolution that we need, right? How far out to the UV do we need to go? How far into the infrared do we need to go? What's the resolution? That kind of idea. And then the vanilla was really about characterization of the potential targets. So identifying targets that are most likely to host detectable, and I very, very specifically put the word detectable in that sentence, detectable exo-Earths, right? So we want to understand that there will only be a finite number of systems that a mission will be able to detect these Earths around for a given architecture, right? So we want to understand the targets well enough so that we can optimize the success and minimize the risk. And then sort of related to this is also the demographics and the architectures of the planetary systems, right? So what's the expected scientific yield for a given mission architecture, given an aperture, given an inner working angle? I added actually outer working angle to this after Ruth's, I think it was Ruth's talk yesterday about utilizing the outer planets to, if it wasn't Ruth's talk, I apologize. Okay. But the point is that these are the sort of the three big categories from chocolate, vanilla, and strawberry, hence the Neapolitan ice cream.
You can't summarize all the gaps into just three flavors like chocolate, vanilla, and strawberry. So he got real quiet. He went off for 5 minutes and produced this slide.
Yeah.
And I was like, hey, that works.
Yeah, sorry. And by the way, anybody who really likes strawberry ice cream probably, doesn't want my opinion on strawberry ice cream. Right. But I would like to point out that how do we extend these kind of categories that we're really focused on the exo-Earths to the other exoplanet wants? And I think that's part of the discussion. What's missing here for the exo-Earths, but then how do these get extended to the wants? Excuse me. And there's probably a large amount of overlap that goes between the two topics. Not a big surprise. All right.
Okay, so back to this question of turning science goals into requirements. So based on the previous slide we talked about, right, we have these categories, but they often overlap with each other on these broad categories. And so here, we give an example of setting requirements for the discovery, aka discovery, or you could call it confirmation or whatever you want to call it, of a habitable or inhabited planet. And Vicky and Meadows and others did a great job of walking through how we could have scales of this. But the interesting thing, if you look at sort of many papers, and most of the papers about habitable planets, they draw these broad categories, right? They say you have an Earth, with some number of molecules and CO, or you have a Archean Earth or a ocean loss, M-dwarf, or you have these things with a bunch of molecules. But when we design the mission, we need to know what the minimum abundance of each of those molecules is to declare that you have discovered or not discovered one of these types of planets. And so often heuristics are used to say, well, if you have, 10% or 1% water vapor in the atmosphere, then maybe that's habitable. And if you don't, then it's not habitable. But we really, want to dig down into how we can set values as a community to do that, because then that feeds into how we actually set the requirements on things like the signal-to-noise ratio and the resolution. Here I show a plot from the poster, the beautiful Barbie poster that everyone got excited about earlier. But it points out that in different eras of Earth's history, with the H2O abundance put here for modern and Neoproterozoic and mid-Cretaceous, you get very different requirements on your signal-to-noise ratio in order to detect that level, that abundance of water vapor in the atmosphere. And so if I say, what's a habitable planet like Earth, you could say, any of these. They were all habitable. They all had life on them at some point. And so we can't just say, well, I don't know, pick an SNR and let's just go with it. We want to drive as a community the process from theory, from discussion at the physical level, all the way to the requirements. And that takes a lot of community input and work on our side. Next.
All right, so this is the last slide. I just really want to point out that, at least in my opinion, that you all are the precursor science team, right? The science that is going on in the community that's going to feed into this. Some of it will be structured and feed, and be, really driven by things that the observatory needs to understand, but also it's just the general sciences going on, right? It is the community effort that will do this. And I think the start will help guide pieces of this, help develop the metrics that we want to do, and all of that kind of stuff. And so sort of questions that we wanted to seed for all of this. We're not quite as organized as the next panel with regards to collecting that feedback. So, but how do we fill in the current gaps that we've talked about? What science goals are missing, and what are the gaps for these? What are other potential exoplanet wants, and what are the gaps that are associated with those, and how do they blend with the gaps that we've already talked about, right? If there's something very specific that you want to do for Jovian planets, can you do that with something that's already being driven for what we want to do for the exo-Earths, that kind of idea. And then something very specific, which is what Avi and Eric have really been talking about in the few previous slides, is what metrics need to get developed in order to fill that. I was about to say in order to fill that gap, but in order to turn the scientific work on understanding those gaps into actual mission design requirements. And so, what are those metrics? How do we do it? A lot of this is also part of what the start is really going to start to drive us forward to. And so these comments at the bottom are really about staying involved, right? This isn't something that's going to be addressed in the next 20 minutes, right? In its entirety, or whatever time we have. It's really a long-standing process, and the start will really help drive a bunch of this, and the working groups that get organized around all of that. And then, of course, there's all this other activity within the individual PAGs. The ExoPAG, of course, associated with the exoplanet program, but also the CoPAG and the PhysPAG associated with cosmic origins and physics of cosmos programs. So with that, unless Jen, do you want to add anything, since the three of us talked throughout the whole thing?
No, I mean, I think it's a good point, especially about the science goals that are missing right now. I think there's, for myself as an earlier career person who hasn't been involved in a lot of mission development, the question of how do you identify those additional science goals? Which ones get prioritized to the level where they are then involved in design considerations and mission development and stuff like that? It's something that it would be nice to see more conversation about, and more, soliciting early and often for science questions or goals that people want to see addressed from the broader community. And so thinking about ways to make sure that happens as part of the start or these working groups is an area that I'm excited to, watch that develop.
Yeah, and just to finalize, first of all, Sarah's taking notes for us, so we are using this as a really broad discussion, but we'll be taking some notes, and we'll be sort of trying to translate those into some of the more direct except style gaps or topics that we want to address. But more importantly, as Jen said, this is for many of the folks who weren't involved in the LUVAR and HabEx and other studies that really trained up certain people on how to do this type of work. We're really have a new start and a new generation and a new opportunity to really rethink some of these. And so now is the chance to, as Jen said, sort of really get asking those questions about how we dig in on these additional science goals and gaps. So.
Yeah, I think we'd especially like to hear from early career people, and definitely stay involved. don't, the concept study teams put a lot of work in it. There's going to be a lot of great stuff to mine from those. Don't feel like if you were not involved with those that that somehow everything was figured out beforehand. We really need to get new people involved. So I think we should just open up
I think with
discussion
that,
at this point.
4 of us are done talking. So, well, that's probably not true, so let's start with the audience or anybody online.
So this is a chance to raise both a big science question or a how do we do this, or how do we get that, or how do I any area that people want to discuss.
Quick reminder: we started a little bit late. What time are we finishing?
We had 45 minutes for each panel, so
Okay.
Hi. So I have a kind of broad question, I think, related to that main goal you mentioned at the start. These 25 exo-Earths that we want to characterize. And from my understanding, that's based on some eta Earth that's basically 25%. And the question I have in my head is, is 100 habitable zones probed really enough? And has the work already been done by the precursor teams for LUVOIR or HabEx or something like that to really understand, how many systems we actually need to probe based on our uncertainty in eta Earth, and binomial probability, etc., to really get that 25 exo-Earths? Or is that like one of the first things we really need to do right now?
I think
Zaki, this is a new comment or responding to that?
So nobody ever looks at the plots and the appendices, but the yield calculations for both HabEx and LUVOIR did take into account a range of eta sub Earth, like the plus minus 1 sigma on eta sub Earth that was produced by the SAG13, exoplank SAG13. So there are versions of those plots that have error bars on them and show the range of yields. And you're right, on the low end, it's too low. Yeah, and you do get 25. That being said, I have heard Bruce McIntosh say that, you really should think about this more as 100 cumulative, search 100 cumulative habitable zones, not get identically twiddle 25 exo-Earth candidates. I have to say, if that's what they meant, I wish they'd actually written that in the decadal. So I'm not really sure what we're supposed to do with that, or how do we just get to decide, or okay.
Yeah, it's interesting. They use the word robust over and over. Now, if you make it too robust, you get yourself knotted up in saying, okay, it must be 25. What is that going to take? And I mean, we could go a very different route in terms of the amount of precursor science, and it may be, another order of magnitude more than may realistically get funded, unfortunately. So, but I think it's probably more viewed as 100 half zones. So.
Can I just follow up quickly?
Yep.
I think that's an interesting subtlety, because really, if our framing is instead on probing 100 habitable zones, then really the science question we're attacking is not necessarily what is the diversity of Earth-like atmospheres. It's more how many Earths are there, and it's an occurrence. Is the occurrence of Earths really the question we want to answer with HWO?
So, a lot of us interpret the decadal as equating the 100 habitable zones and the 25 planets. So the START team is going to have to decide, do you accept that equation, and are you willing to move forward with it? We as a community working with the START team has to decide if they want to go through with it. That was allowing for what the decadal understood the uncertainty of eta Earth to be in 2019 when they received their last formal inputs. Well, eta Earth has evolved a little bit. For example, the Bergsten et al. Result that shows that probably there's a lot more of the mini Neptunes in the habitable zone than Earth if you interpret the Kepler statistics in a certain way. So I think the question for the community is, have we already used up the wiggle room that the decadal survey gave us in that twiddle 25 with some of the newer results on eta Earth that have come out? and thus we are really in a corner like, Aki was worried about. Or can we still live with 25? We're going to have to decide that as a community working through the start.
And for folks who haven't read the ExoPeg announcement that went out this morning that had the abstracts for the precursor science call, one of the selected projects was a program to revisit Kepler and do a new exoplanet catalog focused on the latest and greatest A to Earth. And so it'll be interesting to see what comes of that and if the error bars get any cleaner or if, that median value shifts a bit as they start looking back at that data in more detail with this specific, I think, HWO focused goal in mind.
Yeah, so Marianne Limbach, University of Michigan. I'm curious if we've explored our ability to probe the habitable zone of binary stars, particularly for systems where the binary star impedes upon our contrast in that habitable zone. And if there's any additional hardware we would need to add to the telescope if we wanted to do this.
I believe there's an SAT award working on wavefront correction for binary systems from a team at Ames, I believe. So, but yeah, the binaries, for the nearby FGK stars, it's something like 40% of them are binary. A lot of them are binaries, less than about 10 arc seconds. So that's going to have to be figured out as to what degree do we do binaries. And I think there's still groundwork to be done on characterizing those binaries. There's a lot of these nearby binaries. There's an orbit from 1966 with no error bars on it, and nobody's looked at it since then for some of these systems. So.
Aki Berber, Goddard. So a few things. One, if the binary separation is very small and they're both basically under the chronograph mask, there'll be additional leakage, but it may still be possible. If the binary separations are very wide and one of them is off the field, then what you have to worry about is the stray light from that secondary, and that will be affected by basically the surface scattered light in the observatory and the surface roughness of the telescope mirrors. For intermediate ones, there is in fact an experimental optic that is actually, I believe, is still going to fly in the Roman CGI in one of the empty slots from, I guess, Russ Belikov at Ames, that in principle should allow you to null two stars at the same time. So there's some options.
I would like to just add that we really don't understand the statistics of the planets and binary stars nearly as well as we don't understand in both directions. We don't understand the statistics of planetary host stars that have stellar companions and the planetary frequency in binaries. There's a lot there that we don't understand. But what we are finding is that roughly the frequency of stellar companions that are hosting planetary systems is about the same as what is found for the general solar neighborhood. So roughly the 40%, 40 to 50%. But those stellar companions tend to be further out than the general distribution, but not at like the 10 arc second separation, although maybe for the closest stars. But separations, instead of the peak being near 50 AU in terms of binary separation, the peak is closer to 100 AU. But that's really early, and we're just now starting to really understand that. And so that's a really excellent question. One of the questions that Eric and I have argued over for a long time is there's a set of potential targets for HWO. What's the unknown multiplicity in that particular set of stars? And that has to be addressed.
So I just want to come back to this A to Earth question. I think I want to encourage people not to get too wrapped around the axle and the exact value of A to Earth and its uncertainties, because, when you talk about A to Earth, what do you mean? Are you talking about the conservative habitable zone, the optimistic habitable zone? Is the largest habitable planet 1.5 Earth radii or 1.4 Earth radii? It's an artificial definition. And the basic idea is we want a large enough sample of things that are proximate to the habitable zone where we think you can have potentially habitable conditions that you can empirically define it. And so, and then the other thing to keep in mind is that there's a lot of other forces that are going to drive the aperture size that have, to be frank, nothing to do with science. And so, if we start, going down this road of trying to be ultra conservative and making sure that we, have a probability of 0.0001% of detecting at least one planet, we're going to paint ourselves into a corner. And so I encourage people to think a little bit less specifically about this Eta Earth question.
I don't think the microphone's on.
Hi, I'm Takahiro Sumi from Osaka University. Back to the binary. As I show you in my talk, one of our colleagues is working on the new type of the chronograph for nulling the line instead of the pointing. So with that type of chronograph, we can calculate binary. Not the triple, but with that kind of chronograph, we can search for the planets around the binary.
Actually, I have a question for Aki, since she brought this up. If a star, is there an estimate yet of how bright a star that's sort of off the field, how dim that needs to be before its scattered light is an issue? I mean, bound or unbound, it doesn't really matter.
Not quantitative. I keep asking Charlie Necker at JPL to do the calculation, but I don't think he's done it yet.
Okay.
We did include in the yield modeling codes a model which was actually developed by Dan Serbu of using an off-axis PSF for the companion, so that we actually compute the scattered starlight from the primary mirror for the companion when we're calculating the integration time. So if the background due to the binary star is too prohibitive, then we don't get to do an integration on that target. But that's both in Chris and mine's yield code.
Hello? Okay. So I just wanted to comment quickly about the Eta Earth problem, and if it's 25 or if it's 100 habitable zones. I think the question comes down to, what do you define as 25 exo-Earths? Like, are you going to consider it a failure if it's 24? Or are you going to, depending on what you're considering, if you're trying to find, okay, is the goal to find 25 that match up with the parameters you have set for Archean and modern and the other types that have been shown in the different talks? Or is your goal, if you don't meet that, are you going to consider it a failure? Or should the goal be worded differently to, we're going to search these many zones for as many as possible?
I was going to answer the earlier question about Roman off-axis. Do we want to do that now Yeah. So just quickly for CGI, you can get some off-axis scattered light plots on the IPAC CGI parameters Roman website. There's a detailed page where we've got some graphs with predictions, but equal magnitude binary, we need, to be at least, say, 50 arc seconds away before it's comparable scattered light to the mean level of the dark hole for our single star optimized coronagraphs.
So to follow up on the previous comment about what do you define as success, and is it 25 or 24? I think we need to not look at the specific number as the goal, because that number is not what we are trying to answer. And this comes back to the conversations about framing this as a science traceability matrix. You want to say, what is the question? If the question is, what is the prevalence of habitable worlds, or how common or rare, to phrase it as a question, and then you can start to say, quantitatively, how well does a given sample let us place a confidence on that? And to give a worked example of this, the Gemini Planet Imager survey, when we were designing this, we optimized it to be able to answer the question, how common are Jovian planets on, 10 to 20 AU orbits. And that was what drove us in that case to the sample size that we did and some of the instrument performances that we did. And we designed it not just with a specific desire for what we were going to find, but so that null detections are also informative. And of course, everyone knows all the ground-based surveys have not found that many things. We ended up discovering one new planet and some brown dwarfs and so forth. But we've structured the sample such that we learned something about the universe. We're able to place constraints on the prevalence and demographics of these planets, even from the non-detection. So in this case, it's not thinking that the goal is 24 or 25. The goal is to be able to make statistically rigorous conclusions rather, about the prevalence of rocky planets or habitable zones or whatnot. And so that kind of statistical analysis based on Poisson statistics, I think, is a better way to think about phrasing these questions.
Yeah, so I understand completely why we're rushing towards and working very hard on quantifying our needs and deriving those, putting those into STMs and deriving not requirements yet, but certainly moving towards requirements. But I want to put in a pitch to keep thinking about disruptive ideas. The window for which you can actually implement a disruptive new idea on this observatory will close somewhere in the middle of this decade, and then you won't be able to go back. You'll still be able to do all the stuff you quantified and wrote down very carefully, but the window of opportunity to have truly new ideas come in is not very long. I heard two things at this meeting. Chaz threw out a crazy idea of having light that's rejected by the coronagraph go somewhere to characterize the star, which is a brilliant notion in my view. And then we heard from Ruth about the idea of using background galaxies as sources for planetary transit, which was also mind-blowing. So let's not shortchange ourselves in the end by being too rigidly fixated on these metrics. They have to be balanced.
Oh, sorry. Let's jump online.
That's fine.
Yeah.
We haven't done online yet.
We have one comment from Chris Stark. Completely agree with Marshall. The issue of the 100 habitable zones removes the Earth from the equation when it is obviously critical to answering a science question via sample size. But we can budget for all astrophysical uncertainties, so there are paths forwards to doing this.
There's a hand up in the participants list online as well from Lee Feinberg.
Yeah, can you hear me?
Yes.
Yes.
Yeah, so I just have a thought. It seems like, there's certain uncertainties. Some of them are scientific, the ETA Earth we talked about. There's also technological uncertainty. And I wonder if some of the tools that we use for managing system resources in projects, so things like mass and power, the way we manage those is early in a program, we require a certain amount of margin, and then we have requirements for the margin at CDR versus PDR. PDR needs larger margins. I wonder if the yield is so critical that maybe a way to think about it is what margin do we need at different phases of the project so that we wind up with the minimum scientific, threshold. And so it's just a thought, but it might be helpful to include that thinking in some of the early architecture studies. Anyway, that's my comment.
Thanks, Lee.
Just so we're aware, the comments were down to like the last few minutes here. So just so that everybody's aware.
Okay. Megan Jaluka, University of Washington. So I think Marshall and Chris Stark both brought up fantastic points about trying to get a statistical sample and that null results are still results. But I think what we want to also avoid is inconclusive results. And so my question is really getting at more of the observing strategy. I think we've seen multiple times the upside down pyramid of how you might follow up on an exciting detection. And Jamie Krause touched on this a bit too in her talk, where you might look at one bandpass, realize you need more information to interpret that planet. And so I'm thinking, if we're going into this and we want to do a survey of a certain number of habitable zones, what if you get data back from one of those planets and it's exciting, but you don't really know what's going on. You can't say, yes, that's an exo-Earth, or no, that's a lifeless planet. Is it going to be difficult for HWO to pivot and take follow-up observations of previous targets before the full survey is complete? I think given the excitement around this type of result, the public and the scientific community alike are going to want to know about those exciting targets as soon as we hear about them. And so I'm just curious about what thought has been put into that.
Yeah, I think we have to remember people are going to be, once these spectra are shown in 20 years, there's going to be a lot of public interest in the interpretation. So I'm worried we're not going to have enough contextual information for interpretation of them. I think we need to think about that.
So I kind of riffing off a little bit of what Jason said, but I really, the sentence on here that really gets me is what are science goals that are missing and what are the gaps for these? And I'm thinking about this also from the extragalactic point of view. And I think there have been, it's really easy for us to sometimes think, oh, this is going to be a much larger Hubble. We're going to do, I've heard a lot of times this week, well, this method has been working really well for the last 10 or 15 years, and, it's going to work great in the future. And I think when we get to this place where we're having a complete change in the parameter space that we're able to probe, that we're able to look at, that the tools that have served us well for the last, number of years are no longer going to be up to the challenge for the kind of data we're going to be getting in 20 years. And part of that's near and dear to my heart is, the theory, the simulations, what the tools we're going to need to interpret some of these data are not there. And so when I look at that second question, it's how do we start thinking differently about the data and the interpretation of the data now, in order to actually be ready for that phase transition in 20 years? And especially if we can start thinking differently about what's coming down the pipe and preparing now, that's when we can actually get in and start coming up with these more novel ideas about how to actually make the HWO be a potentially, more disruptive observatory, to use Jason's word, than, just a larger Hubble with, larger instruments on it.
Yeah, how many more do we want to?
She's had her hand up for quite a while. And then Jen also has her hand up.
Thank you, David. Maggie Beth Turcott, UMaine, NASA intern. My question, because in exoplanet talks this week, there have been discussion on M dwarfs, as well as FGK. For the sample that you're going to be finding the 25 exo-Earths from, will that be including the broad range of spectral types from F to M, or will it just be focused on FGK?
Very limited by distance and brightness. So our initial crack at it was only a few M dwarfs. If the inner working angle gets more aggressive, keep pushing inner working angle, you can pick up a few more nearby M dwarfs. So.
Jen had her hand up for a while as well, and then we should think about transitioning over because it's almost 5 to 12.
Yeah, I'll be quick. In response to, I believe, Megan's comment just now about if we see something that looks like a potential exo-Earth and we want to revisit it, how does that fit into the scheduling? This is an adjacent effort, but this is one of the reasons why we've been trying to suggest beginning precursor surveys of these stars now, both to try and identify stars that are unlikely to be able to host habitable Earth-like planets because there's a disruptive giant planet in their HAB zone, so we could deprioritize those from the list. And if we get a little bit more development work done, starting to do things like extreme precision RV surveys to look for hints of temperate rocky planets around these stars, because that could then allow the prioritization of those targets early in the mission lifetime, and then you would have more flexibility to revisit them instead of finding a thing that looks promising right at the tail end and then potentially struggling to hit it time and time again to broaden the amount of information you have from HWO observations of it. And so I think the early work on characterizing these systems to the best of our abilities is a priority that we should be thinking about because it would help with these kinds of efforts.
Just to mention, I think it was Rhonda Morgan's 2021 SPIE. Basically, if you know where to point ahead of time, you can speed up the HAB zone exo-Earth yield. You'll get the same yield, but you get it faster because you know where to point. So.
All right, I think we need to actually transition here. We've already eaten into the time for the other panel.
So one thing you notice, there's a lot of great comments online, and I encourage everyone, of course, everyone's very online right now. You could go and continue the conversation on the Blue Jeans chat as well. So,
all right, we really appreciate all you guys' input and participation, and apologize to the next panel for eating up all your time. Do I need to like put something up for you guys?
Yeah.
Okay.
Just drop your slides. And then I got it.
Okay.
So we're just going to jump on in while Rachel gets things going. I think first we'll very quickly introduce ourselves, and then we're going to lure you into participating, which you are already well warmed up for. So do you want to start us off, David? Sure. You have, yeah. Mm-hmm.
David Ardila, Exoplanet Program Office, JPL.
I'm Sarah Tuttle. I'm at the University of Washington.
You Swara.
Okay, I'm Swara Ravindranath. I'm the Deputy Chief Scientist for the Cosmic Origins Program from NASA Goddard. And I also want to mention that Peter Kurczynski, who is the Chief Scientist, is also here, and we'll be more than happy to talk to you about what the Cosmic Origins Program does and what opportunities are there to participate in the studies and program analysis that the Cosmic Origins Program Office facilitates or is funded through the Cosmic Origins Program Office.
Hey, and I'm Rachel Beaton. I'm an assistant astronomer at this institute, Space Telescope Science Institute, and I will be taking the role of scrolling around our mural. I'm on the COPAG EC, and I'm the chair of the STARS Science Interest Group.
All right, so I'm going to kick you off. So if you are on the mural, excellent. If you are not, you can watch as Rachel plays along on the screen here. One of the roles I'm here in is running a UV technology working group in which we're trying to kind of draw together many of these topics we've been talking about today, right? As someone has thoughtfully put here soon, architecture needs to be coming soon, right? We're thinking about instruments, but we're still trying to pull together our various science cases. And one thing that I think Lee Feinberg just mentioned, which is important here, you've heard language around STMs, around metrics, right? And so we want to introduce you to one way that we often use when we think about missions to lead us to our mission models and our mission parameters. So science systems engineering, David, do you want to do your quick intro spiel?
The science system engineering term was invented by Riccardo Giacconi, who was across the street and was one of the pioneers on X-ray astronomy. And it is a way of thinking about...
He was here.
Right.
He was more than there. Just...
Right. Thank you for the correction. So, yes. So it's a way. Although I don't think he thought about as a structure as what we are going to present here. So as it has been mentioned before, we need to do science traceability matrix, and so these are the steps to do science traceability matrix. So we need to have a specific question. We need to have physical parameters, we need to have observables, we need to have instrument parameters, and we need to have mission parameters. And with these things, we can map these to a science traceability matrix. One thing that is important to know is something that Abby already mentioned, is that people have different skills in different places, in different of these different boxes here. So some astronomers are all about the observables. We want to observe these stars, we want to do and this is one of the cases from LUVOIR, main sequence turnoff in B and G from color magnitude diagrams from result population of stars. Other astronomers are more about physical parameters. In this case, we want to do age and metallicity. And welcome to numbers.
Don't look behind the curtain. I'll fix it. Where'd it go? There it is. Okay.
Okay. And so it is okay if your inclination is to look into certain of these boxes and not into others, right? Completing this whole row takes a village, takes multiple expertise from multiple people. So, and at the end of it, you have a complete row, and it's in the particular example from LUVOIR, the question was, how does metallicity control star formation rate? The physical parameters were age and metallicity. Observables was the main sequence turnoff in V and J color magnitude diagrams. The instrument parameters was effective area, filters, instrument noise, PSF size, field of view. And there are mission parameters, which are total observing time, repeats, pointing, stability. And from that, you end up with a statement. All these things have to be eventually very quantitative, right? It's very important to be very quantitative. And you end up with this yellow statement, Rachel, that maybe you can show, which is, we have used the term metric a lot, so this is a science metric. We want to determine how metallicity controls star formation rate by measuring the age for objects with ages between A and B within 8 gigayears and B gigayears to X% precision, and metallicity for certain value of F over H between C and D to Y% precision of resolved stellar population in N galaxies within F megaparsecs, right? So you have to end up there. It is important that you have very quantitative goals. But it takes a while to do this, and it takes many people to do this. And this is important because at some point things are going to become very hard, right? We are going to discuss changing the characteristics of the observatory, maybe reducing the aperture when there are cost constraints. So you need to know where your pain points are, right? And the other thing that this helps you do is to determine what really is driving the observatory, right? What are the science goals that are driving the observatory? Not all science goals will drive the observatory, right? Which is okay. But we need to identify which are the ones that drive the observatory. We know the identification of the temperate Earths drives the coronagraph performance. We know that for sure. But for the transformative astrophysics, it's still unclear which cases drive the observatory. Maybe so. We want to particularly focus about corner cases, right? That was a long spiel. Sorry.
Oh, it's good. We're good for long spiels here. So, if you're in the mural, I would encourage you to start looking at what people are adding. That was an excellent context. And what you'll see is it's actually really hard to fill out these individual squares, right? So just do it. You're going to be terrible at it. That's great. You should be terrible. We put in some terrible examples yesterday, so you should use those as sort of like your spiritual guides. There will be no judgment, although occasionally I'll put, snarky response questions on them, as you can see there. But
yes, and I've been trying to fill out for exoplanets what everyone was commenting on in the last session are actually things you can write down here.
You can put them there. And I think what's important to talk about is that, as David was mentioning, I'll take a quick survey. We've talked a lot that, many wonderful speakers have mentioned we should be in the UV. That should be happening. How far into the blue, and Kevin can't vote if you're here, how far you can use words or you can be qualitative or quantitative, and you can just shout out, we're getting near the end of the conference. How far into the blue should we go? Okay. Any other votes? How far? What, 900, 1,000? Wait. Any other votes? Just shout out.
912.
I wonder why. Yeah, this is like let's make a deal. No. Right? So in general, when we ask, the answer we get is we should go very, very blue. Let's call it around 1,000, right? And why should we go that blue?
Science.
Give that man a drink. You should do it for science. Huh? So the trick with transformative astrophysics, which is to say everything that is not the statement that you're going to fight about, is it 100 habitable zones or 25 exoplanets and what does winning look like? Everything else in the universe, we're going to get some of it and we're not going to get all of it. And if there are pieces we want to make sure we get, we better know when we lose it. Right? So if you think about transformative astrophysics or the universe, you can think about a circle with an edge. Lots of stuff is going to fall into the circle almost no matter where that edge is, But we want to use these various tools to determine those edge cases. So when someone shows up and they're like, I get why you want to be down there, sure, far UV, sounds very exciting. I'm thinking we can probably get to like 1500. We need to be able to say, here is what we'll lose. Here's the science we have to do in this generation of telescope. Here's the list, and here's why it drives these parameters, right? Here's why it drives this piece of the telescope design. So something that we're working on, and many people have done this in different frameworks, with LUVOIR, with HabEx, right? There's places where a lot of these pieces are. One of the things we're doing with the UV Tech Working Group is really bringing that together so we can find those edge cases. So if you have a piece of science or a piece of technology and you are like, here's where the edge is, I can do this, but if we move this way, I cannot. That is especially the stuff we'd be excited to see you populate this with, or to ask questions about now, right? Because I do think the thing that maybe some of us who are middle-aged, one of our fears, right, is that doors do close on these things, right? And then we're moving on to whatever comes next. So there is nothing sadder as an instrument builder to finally making progress on your design. You start cutting metal and doing things, and then you go to a meeting and someone's like, why aren't you observing my wavelength? You're like, fuck. So that's how it feels. So this is the time, right? We will not get all of it. There are things that we will lose. It is compromise when we build instruments, but we really want to have a community understanding and a community conversation about how those decisions are being made, and to have a really robust conversation about that transformative science that is going to be moving our fields forward for a very long time, right? And as you may have noticed from Rachel's excellent work in the yellow section, a lot of exoplanet work, and we split these based on decadal categories. Up in the corner, you can see the list of decadal categories. We didn't make you look at them because it's too late. But there's a lot of exoplanet science that, like, the way I've been thinking about it a lot these days is there's the coronagraph, and then there's the other instrument, UV spectrograph IFU, right? So when not just science separation, really, because a lot of interesting exoplanet and exoplanet adjacent science is coming out of that other instrument that's not the coronagraph. And it is important for us to keep those connected, because the primary science of the coronagraph will do much better with a robust UV spectrograph as well. Right? And so trying to sort of keep that communication open is also important. So I think part of the crux of this meeting is, even though we all speak in like very different dialects in this room when we look at our science, we're bringing that together so we can find that common ground to connect these instruments through this observatory. So do people have questions either about Mural, which I'm sure you all use every day and so are comfortably navigating, or do you just want to ask questions or say things out loud? You don't have to just use the Mural. You're allowed to use your voices. You're not muted here in this room or online, which I can't really see very clearly. Online, they are muted. Cruel. Do people have questions about this or things they are excited or worried about? Okay, Jeff, and then, yeah. I know who you are. No. Oh, you want a microphone? Be loud.
Just for the people online. So given the openness of this, right,
Yeah.
this observatory, the HabEx and the LUVOIR studies had reference instruments. And maybe the decadal was pretty clear about having a chronograph as a baseline, but they were not as clear about what kind of instruments here. So the science cases here, there's always a chicken and egg about what could I do depending on sort of a nominal kind of instrument. And so I'm curious how you think the community right now could diversify or the kinds of instruments that this would have, or do those previous studies kind of capture the right suite and we should be focused on that, as the previous 5 years of work sort of highlighted that those were the right kinds of instruments?
I certainly think that work provided a really robust collection of instruments that have been well studied, so we really understand what we would get with that instrument suite. I think one reason why we thought doing this little chunk this way would be useful is to give people a little bit of room to think more expansively, to see, are there pieces that are falling well outside of that instrument suite, right? I think there is absolutely a balance where the LUVOIR and HabEx work was really crucial for laying the groundwork and for seeding the decadal, and it's not binding as such. And so there is some room for expansiveness, especially if people have things they know cannot be covered with those instruments. Aki.
I guess following on from that, a question that occurred to me today for the first time is that I hear some people are talking about a UV multi-object spectrograph, and some people were arguing today for a UV IFS. And I would like to understand why. Like, what's the real difference between these two instruments in terms of your science?
Great. So that's something we should capture in the mural, first of all.
Why don't we have
I think someone's taking notes for us. Is that true?
Yeah. Well,
that was the rumor, but now it appears to be. Ben, take notes. Come on. So
whoever's taking notes, take them in the mural. This is our
good idea.
recording zone. We can have a space for what is the difference? What are the science trade-offs? These questions are all fine, but just put them down into the mural.
Yeah.
And then other
dump them. We're going to capture them.
And Swara maybe want to.
Oh, to do that. Yeah.
Thanks for that, Aki. That was one of the things that really stood out in the last couple of days of this conference, which again has been amazing to start these discussions. And I completely agree. That's one of the things that we need to study, what the trade-offs are there. And it really, it's for the community to say, how much of their science can be done with one or the other instrument. And while I have the mic, I also want to go back to something that Jason mentioned earlier, that this is our opportunity to think out of the box. And the very fact that we're all here in this room and talking about the Habitable Worlds Observatory is already, showing us what the community can do, right? So now is the next step where we can actually define what instruments, what we want to see on the observatory. And, this is where we really need community input. So definitely when you think about trade studies like this that you want to investigate further, we really welcome the community to get involved in those studies. And if there's something that the Cosmic Origins Program Office can do to facilitate that study, then please reach out to us.
I also just really briefly wanted to reply with the why not both GIF, right? That they're not necessarily exclusionary, and we are able to, depending on what the science drivers are, one can imagine sort of having functionality in different ways depending on what your science goals are.
Yeah, and if you have a strong case for either type of spectrograph, go onto your science area and put down instrument parameters and put down IFU versus MOS and write your science question or your observable. You don't have to fill out the whole row. You can just write down what you think is interesting or what you would like to see and let the community crowdsource that information. Someone has a science case for the instrument you want to build, and someone wants to build an instrument for your science case. But let's get it down, and we're going to try to moderate and pose little questions, the little boxes are kind of do you mean spectral resolution or spatial resolution? To kind of clarify. And this is what we want you to do to get the community feedback. We don't have to discuss every question in front of the room. We want to get it written down, and we want everyone to participate. We all know that there's studies out there, but this is about participating because we're in a room where we can participate. So get on there. Yeah, IFU. Good job.
Yeah, so I want to comment on one thing that I see is a bit missing in this meeting is polarimetry and spectral polarimetry in general. And I'm actually not really sure why is that. So we will try to build the next generation telescope and observatory to get discoveries of the universe. And we haven't really looked at polarization so much. And I know it's hard to probably interpret it, but there is a lot of information and a lot of discovery potentially there. And it's not really on the table of discussion, at least from what I've heard in this meeting. And maybe there is a knowledge gap on but people don't really understand or know how to use it actually. And it's always a circle, right? You get observation which you don't understand. You need to model it to understand it, and then it circles. And if there is no, like if the circle is broken and if there's no observation to trigger the questioning, then there is no increase in knowledge, and then we don't know how to use it. So yeah, I just want to bring this on the table, that maybe spectroperimetry is an interesting thing to have, because we haven't looked, especially in the UV. There is no such thing, essentially, except on some rockets and things like this. So
We have that flagged in our COPAG breakdown of decadal questions to instrument capabilities. Polarimetry is there a lot.
Aki, did you want to answer that some, or did you have a different question?
So I can say something about the spectropolarimetry. Okay. Yeah. So during the LUVOIR study, for those who, you may already know this, but for those who don't, during the LUVOIR study, CNES did a contributed instrument study, and it was in fact an ultraviolet spectropolarimeter called Pollux. They did, however, only design it for LUVOIR A, because the feeling at their thought at the time was that good spectropolarimetry would not be possible with an off-axis telescope like LUVOIR B. But being off-axis is advantageous for the coronagraph. To be quite, if that is true, if you cannot do good UV spectropolarimetry with an off-axis telescope, then I don't think you're going to get it. Possibly, unless, I don't know, maybe things will change with the coronagraphs, but, you know, I think that must take priority. So.
You're going to do all the work, David. He was here, but he's
one of the things that this exercise is good for is to understand what are the unique questions that polarimetry can answer, and then we can decide whether those are questions we want to answer, right? It may be that there are other questions that are more relevant, or that there are other instruments that can give us smaller error bars in whatever science topic we are thinking about. But this provides us a structure to think about this.
Right. And so if you have a science theme that you think about for polarimetry, it'd be great to put that down under the theme. And you've got the instrument, and you've got the potential mission constraint, which is on-off axis telescope. But we need to know what the science question is. Does that make sense?
And I'll also point out that, you know, one exciting thing about doing the exercise this way is that, you know, let's say for argument's sake that it effectively is out just because of some other design choices and trades that have happened, and could be extremely complementary to the work that is happening when HWO goes up. So Evgeny had this presentation that I missed some of, but had this idea around, for example, small sats that might have standalone instruments that would be complementary, that wouldn't need to be integrated into the suite of Habitable Worlds, but would be kind of interactive in that way that might fly at the same time. So that might be exactly this kind of thing that would go in that direction. I think we have someone up here.
Yeah.
Oh.
Can I? Okay. Yeah. One of the points we have not discussed at all is the long wavelength cutoff of this. It's UV optical IR, and IR, you know, we get this mission in the 2040s. We want to have a big mirror to do J-band, H-band for another, I don't know, 30 years after that, right? And a lot of science depends on that. With C3 IR has done a lot of great science. You know, we have to discuss also that capability, I believe. And you just said it, the other thing I wanted to mention, flux calibration, wavelength calibration, things like that, thinking about constellations, CubeSats, things that can assist at L2 to do that type of thing. Have calibrators, for example, and, you know, I've heard about it, but I don't know if it's feasible. I have no idea if we're thinking about in reality. So just bringing those two to the middle.
Absolutely. And
Julie and then Mark.
I think you said there was one online question, so maybe we can
There's
do the
a
online.
comment online from Michael McElvain. Totally agree with Brendan's comment. It's clear from this week's talks that we need significant science margin.
I don't have a science statement other than just start and the tag. Discourage any particular science case because during the start and the tag time frame, we're not prioritizing, we're not down selecting, we're not encourage all science cases put up there, regardless of what architecture it requires. Remind people of that. Thanks.
That's a great reminder. Thank you. And again, I think that's, part of what we hope for with kind of this broad brainstorming approach is, right, feasibility is not crucial. It's not, someone told me we shouldn't do this. Like, put it down. This is the time. Like, this is when the window is open.
Mark Postman here. So actually, to follow up on Julie's comment, I agree this is a great time to be blue sky, but at what point does that science prioritization come into play? Because imagine someone comes up with a really spectacular idea for spectropolarimetry. We have a really spectacular science goal of searching for habitable exo-Earths, and the configurations of those two may be incompatible. So at some point, someone's going to have to say, this science trumps that science. So when does that happen?
Well above my pay grade.
That happens in official pre-phase A. We are in pre-phase A right now. We haven't even started pre-phase A yet. So that once pre-phase A officially begins, which is after the start and the tag end, that's when so part of that is NASA and the pre-phase A project. And we don't know who that is yet. Okay, so and so it is hopefully the job of the start and the tag together and the community, the global start and tag, to write down say here's my analysis of this science with this particular architecture, and I need to what are the architectural or instrument or observatory breakpoints for that particular. Each and every science case. Of course, we're flowing all the science cases from the decadal. In the area where the decadal was fuzzy, that's okay. They weren't supposed to do everything. So that's the job of the community, but we are always flowing from the decadal. They said they address 2/3 of the, HW addresses 2/3 of the decadal science goals. Well, we need to look at each of those goals and say, okay, and then make this Venn diagram of what are the in common type of instrumentation / observatory capabilities that each and every science case needs, and then where are the outliers, and we need to understand the pros and the cons of every single science case and their architecture needs, and that it is the community's jobs to make the cases for each of those, and at a future time, we're basically going to be giving them decision memos. Here are all the different things you can do with this kind of science, and here are the hardware and software needs of that. So yeah.
If you are having technical issues with using the mural, you can just go to Thursday morning talks and put your stuff there, and we'll take care of it.
So I'm going to be a little provocative and maybe ask Rachel to zoom out and show the whole mural for a second here. We're filling out the exoplanet column, and it's a Habitable Worlds mission, but a rising tide lifts all boats. This has to have as strong a case across all these areas. I think one of the strengths of JWST is it's not just an exoplanets mission. It's not just a cosmology mission. It's an everything for a huge fraction of the field mission. And we've had a lot of discussions on exoplanets this week. I'm super excited about those. That's what I do. But we need to collectively fill out the rest of this, as well as we're diving into the yellow chunk in the middle. Just my 2 cents.
Yes, and if you are in Cosmic Origins, your PAG is here, your reps, a bunch of us on the committees. We're happy to have you participate and continue these discussions through the PAG structure. We'll post those links in the Slack maybe for how people can sign up for the mailing list.
Just in connection with that, I just wanted to say, so the Cosmic Origins program has various science interest groups. We have 5 science interest groups on stars, AGNs, galaxies. So we really want involvement from the community. So we encourage you to either go to the website or please come and talk to us, or, spread the word and really get the community involved in right now, particularly the early career researchers. I mean, we really want them to be involved in this. You have not missed the boat because you were not part of the, LUVOIR or HabWorlds study. You still have the opportunity to put in a pitch for your science and the kind of instruments that you want to see on this mission. So, encourage you to come and talk to us.
So, hi, this is Leonidas Moustakis from JPL. There's some science themes. One that we haven't really touched on during the week so far has been the nature of dark matter, where we do expect to make an enormous amount of progress over the next 10 years. But, the fact is we're not going to, even if we discover a lot in the next 10 years, there's going to be a lot more to figure out. The more we learn, the more we're going to have to dive deeper. And that's a really big, broad topic. No single observation or single target is going to really nail that. There's going to be things we're going to learn from resolved stars and dwarf galaxies at huge distances in the local volume. There's material that we're going to be able to do, or work we're going to be able to do at very, very high redshift with the kind of resolution sensitivity of HWO, and tons of things. So just looking for discussion or maybe some guidance, you can't write a single science case for big picture questions like that. And there are others like that too, of course. Any thoughts on that? How do we start capturing that in this kind of a science theme driving to requirements when there's so many different facets to a fundamental problem?
So, I think that's one of those things where, it would be captured in multiple rows, in this instance, or in multiple rows, depending on, for example, the target. So the overriding science question might be specific to dark matter through the observable of particular kinds of objects, right? And so, because what's driving the design is not, at some level, the dark matter, but how we are trying to observe it. Right? And so I think that's sort of how we capture that.
So I wanted to kind of jump back on the thing that I've been harping about. And I sort of just want to kind of look at these science questions and ask how many of them, how do we make them more hypothesis driven? And that's because, again, when you ask how do we get to quantification, actual numbers, you actually need to be asking where the threshold is between proving one hypothesis or disproving it in that sense. And so when we ask what is the nature of dark matter, I think a better way to pose it would be, is dark matter cold or hot? Does it follow the WIMP model or the X model? I'm not a dark matter expert, obviously. But I think we need to, there you go. Okay. Great, but yeah. So, but I think the reason is it's important to pose it this way because we can ask what the threshold of galaxy formation is today. Now we can look with the Hubble Space Telescope.
No, I wrote a whole proposal about it. We can't, but let's talk about it later.
But so the question is, we can't because it doesn't do X.
Because we need something called Roman.
Okay. So I guess my point is that if we say the threshold is deeper than we can go, or we need more galaxies, it's because you're not disproving or proving what the current hypothesis threshold is for that. And so I urge people because I'm not the expert in the question, I can't get down to the actual numerical value that it should be. It really relies on the people who are actually posing the first questions to really pose those hypotheses that we can get at.
But we want everyone in this room to enter with their question. The more complicated stuff is what we have huge committees that meet every week, and we talk and we work on this. We also have the decadal questions, which We don't want to scare people with the decadal. I spend a lot of time thinking about the decadal, but each one of these questions, oh, here, these have the sub-questions, have all these sub-questions that have sub-questions and sub-questions and sub-questions. That's what those of us serving on committees are going to work with. We want everyone to enter with their ideas, their feasibility, their technical thing, and we work it out. And then we'll have this long, ongoing conversation. We have all of START, right? To work it down to that and also make it explainable and presentable at future meetings. Basically, we need all of astrophysics, which also includes exoplanets, to get caught up to the question, to the statement, we need to find 25 Earths or whatever it is, right? This is what we're trying to do, but we want everyone to come into the process, write their thing down. Don't worry so much about some of the nuances, some of the details. Write that stuff down, and we're going to help you do that. That's what your committee is here to do. That's what Sarah's on the UV working group. They know the details of the coatings and the lithium and the fluoride. And
the lithium and the fluoride.
And the fluoride. We're putting together the community. This is a community process. We're putting together the community to put this all together, and we want to make sure everyone can participate and enter. And the barrier for entry is somewhat anonymously posting your idea on the mural.
Yeah, I mean,
this is where we enter.
Let's be clear. There's an icon of someone surfing on a shark. Like, it's a really low barrier for entry, friends. Like,
yeah.
Like, it's really, you can do this. And I do, I think it's important to recognize, absolutely, right? The things that we can use are the numbers that create kind of that boundary edge, right? And being able to record that and being able to collate that along with what has happened before and feeding that all into the START to be able to do that evaluation to eventually move towards an STM for this mission. There's just, this is a midpoint in the journey, right? But I also do think it's important for many folks who, the first time you see a science traceability matrix and you're just like, what is happening? It's like, write your thing this way. And you're just like, yeah. And so I think that part of this too is to encourage you to start practicing that a little bit, right? Because we do have a lot of exciting missions, not just HWO. There are a lot of other ways to get into questions as well. We love building giant space telescopes, but we love building other things also. And so when you can get down to these columns, the mission parameters columns that are tiny now, but maybe big on your screen, when you can get to the mission parameters, that's when we can really talk about what's possible and what we can build and what kind of trades we're making. Right. So that's where we're trying to go.
Because going to the summary statement that David put for his example, you notice there were like 6 parameters in there that you had to fill in, A through F. That's 6, I think. Like, that's a whole 3 to 4 year science investigation to fill out, right? We don't have to do that in a discussion section at a conference on a Thursday when the ozone's going to get really high and it's going to be 96 degrees Fahrenheit, right? We're brainstorming today, getting it all down while it's fresh, and then moving forward to the community because we have these precursor science calls, we have our START committees, we have our program offices. There's lots of ways to keep moving the conversation forward, but we want everyone to enter with their Post-it.
All right. I bet everyone's hungry. You have to stay here till this is done. No. Does anyone have any last questions, logistical questions before? Yeah. Yeah, you can totally do it tomorrow. It does not self-destruct, and let me tell you, this is not how I'm spending my week. So we've got plenty of time. Yes. Steve, yes.
No, okay, I just want to say.
Please hold. Put a microphone on him all time.
I just want to say that the great thing about being the old guy is that there's lots of youth who have stepped up to take this role on, and they all deserve a big hand.
Also, I really appreciate watching all your cursors run around here. It's like the joy of my day. All right. Thanks so much, y'all.
Thank you. Thank you. A little bit, I'm going to say these things at least 2 more times, okay, just because everybody needs to know the important information. There's a set of dinner badges, which is your ticket to get into the reception tonight. Those are at the reception desk. And if your name is on one of those, you're good to go. Just pick it up and bring it with you. The shuttles will be circulating from here to the hotels and back in a continuous loop between 3 and 3:45. So if you want to go back to your hotel, drop your bag, change into your good clothes, that's your window of opportunity. They'll be operating continuously. Make sure you get back on one of them. By the time it's 3:45, 3:50, 4 o'clock, that it will be too late because we'll be back here on the buses. Now we have a lunch break. We're doing another do-it-yourself session this lunchtime where we have Rhonda's in the back doing her simulation tool demo, and then we have Nicholas Flauget talking about sustainability and climate change and the relation to our big missions. That's starting at 1 o'clock right here, and it should also be online. Rita, did I miss anything? Wow, how did I do that? The buses leave here at 4 p.m. and then at the back end on the trip back, they'll stop at the hotels. So you won't have to arrange transportation between here and your hotel. Sorry? The buses will stop here and the hotels. That's what I meant to say. Yeah, the buses will be labeled with the hotels. Same. Parking for Tech Day is the same as today. Yeah, that's the right time. I don't know what I'm doing, so I'll get Thomas to come.
I can also come back in 10 minutes.
He's got to work his way down Price is Right style. Question. Glad you asked it. Good question. Glad you asked it.
Thanks. I have a question not related to that.
Okay.
I should not go to the.
Yeah, that's right.
I just wanted to double check, make sure if I need to be there.
Oh, you definitely don't. No, so that was invited.
Yeah.
Sorry, I forgot.
Fine. I just wanted to double check.
No one's expecting.
Okay.
That was a good question. It's great. Great fearless behavior to ask questions like that. Just want to make sure.
Admin writes in the computer.
I just want to make sure the goals we're setting don't assume the answer.
Yeah. That's good to. You're here for that back and forth.
Yeah.
Yeah. Are you the only speaker? Does Nicholas also have slides or not?
I also speak to you on an email. Yeah, it's one of the people that was asking from presenting at Goddard. When I read the when I read an email, she said talking about the fall, and maybe each time.
We'll figure it out.
Yeah, I just wanted to. Oh yeah.
Yeah. Disable your audio. That's odd. So if you
we have a lot of frameworks. Nice.
you can just thin that whole piece of this area.
Even for years.
Yeah, these are then people can see to yeah, all in large GTR.
Okay, and then where do I put my computer? I'm excited to get it. Right here. Good.
Yeah. You're at 1 o'clock now.
Right, 1 o'clock, 20 minutes.
So you're gonna leave your computer or you're gonna
I was gonna leave it.
For
I'm
sure.
gonna plug in the power in.
power off now. Okay. Is Nicholas also gonna use this?
I don't know.
Okay.
Okay, so I should stop sharing for now, right? Until we're actually back from lunch. Okay, so I think that's all set up. Good. I should lock my screen. Thank you so much.
Where did the meeting go?
Yeah. Yeah. You wanna run that anything together? Can I just plug in the way? And she's running blue. Yeah, I can also connect on machines, right?
Okay.
Sure. That's good? Yeah. And so basically you select on the screen my presentation to print or whatever. I mean, just share. I just share. Okay, no, wait, okay. Yeah, fine. Yeah, I'll do that.
Oh, yep. The mic.
I do. Is the audience also is it interactive?
No, they'll do stuff on their computers.
Share your screen so that
Yes. And that screen testing. Do we have a facilitator or do we just get started? All right, I'm going to get started. Hi, I'm Rhonda Morgan, and this is an interactive tutorial in ExoSims. Now, this is a shortened version of a 1-hour tutorial that was given at the Yield Modeling Tools workshop that was held about a month ago at the AAS meeting. Now, when you have a yield modeling tool, you need to do a few things. You need to have a model of what you're going to measure, a model of how you make that measurement, and then a model of the mission, which contains the constraints under which you are optimizing mission resources, which is usually exposure time, but can also include things like fuel and consumables and or hardware lifetime. So the way that ExoSims works is that we have an input star list, and then we synthesize planets around those stars by making draws on probability distributions that describe the properties of those planets. And then we actually simulate a mission and the observations in that mission. So we'll take a look at a target and calculate the integration time and signal to noise for that, and then make a decision about how to optimize the rest of the targets based on what we find there. So it is dynamically responsive to the results of the observations. And it's scheduled, and it abides by realistic mission constraints like solar keep out. And then we repeat this for multiple universes, and that's where the Monte Carlo comes in. We do it over hundreds of universes. And so then the yields that we output from that are actually probability or, posterior distributions. And usually we just report the mean on that. So what goes into that is, of course, the starlight suppression system performance, as well as the observatory design and its field of regard and its keep out, for example, for Roman, where the radiators are placed, put a really strong constraint on the anti-sun angle, as well as the orbit design. and then our rules for observing and our logic for selecting targets, as well as an optimization engine. And we output from that yield posteriors. Now, the framework of exosyms is modular, and it's designed to be this way so that you can modify or change any one of the modules without having to impact any of the rest of the code. So, for example, here are some of the current existing different options for modules, and I'm going to look down here at the planet population. So you can have the planet population that Bob Brown used in his 2005 paper on completeness, which is a uniform distribution of 1 Earth radii Earths. Or you can have the SAG-13 distribution, or the way that was modified by Doles and Plavchan. You can even have the known RV planets that are downloaded from the NextSci website, and it'll go do a fresh download for you anytime you ask. And you can make up one of your own. You could say, I really like Jupiters, or I really like sub-Neptunes, and I just want to know about only sub-Neptunes. Now, some of these are color-coded, and that's because they need specific simulated universes, which is this box over here. And that's really about how you build the universe from those properties. So some of those need to be correlated. But really, the backbone of the whole thing is the survey simulation. And this is what has the observing scenario and what has the mission scheduler in it. So with that mission scheduler, once I have my posterior of yields, I can do things like plot as a function of mission time what the yields are, how quickly I get them. And that's useful because, starting on this left plot over here, this blind search is the usual scenario that we're used to thinking about and that HabEx and Louvois reported in their final reports. But I can also look at what's the impact of a hypothetical EPRV instrument and if we had prior knowledge from that. And that's the second line of having prior knowledge. And we can see here at the beginning that the gap on that is significant. At the beginning, we can get spectra right away. That's exciting for the scientist and for the public. And then if you find anything interesting, you've got more mission time left to do follow-up observations with some of the great ideas that we heard about here at this conference, like looking for glint and being able to look at multiple different phase angles so that you really understand your phase function and the atmospheres, et cetera. So it'll give you, now, eventually that levels out to the same slope as your blind search because you've used up all of your EPRV prior knowledge. But there's an offset there, which in essence, having EPRV data is like giving you 2 more years of mission time. That's pretty significant. And then this top plot I'm going to mention because this is the cheat mode, which is I synthesize these planets. I know where they are. What if I just give all that information to the observatory and I look at what it would take to skip the blind search and just do characterizations? Now, this would not happen in reality. We would never have this good of prior knowledge. But it is an important check on the capability of your spectral characterization, observing scenario approach, the metric that you want to use, while still abiding by mission constraints, like where the observatory is at that time of year and solar keep out. And then you can do other things with this, like, well, let's look at the metric. Sure, the left plot is the water search metric, but we could say, well, what happens if instead we want to try an ozone, where we have to double the spectral resolution and we have to almost double the SNR? That's the middle plot. And then the right plot is, well, what if we want that broad bandwidth spectra over the visible, and we're going to build that up in 20% sequential subbands. So those are the kind of things that you can do with a yield code just to get to yield answers, and this is for a 6-meter coronagraph. And those different metrics could help with trades between different architecture options. So you might think of that as a few or a handful of options, where you do all this deep analysis on the metric and roll it up into a single number or two. But there are some other things that you can do where you can actually, through a lot of perturbations to your architectures, you can explore the whole trade space and try and understand what is the morphology of that trade space. So like, what are the parts of that trade space that you're never going to get to? Or what are the really expensive parts of that trade space that is just a fantasy? But most importantly, you can look at what your Pareto front is, right? And you can see how close are we to the Pareto front, right? Are the 5-point designs that we're considering, are they anywhere near the Pareto front, or can we consider something else that'll be a little bit more optimal? So I hope I've excited you with what you can do with a yield code, and now I'm going to start the tutorial part of this. Now, if you want to play along, what I'm doing is a web-hosted Jupyter notebook. And to help you find it, I have put it into the Slack, but you can also just search for the exoplanet Yield Modeling Tools workshop website. This was a workshop that we held about a month ago. And while I'm here, I do want to point out, let me switch over to the web now. I do want to point out that there are a lot of concepts that go into yield modeling that you have to get right in order to have reliable yield numbers. So we put together a set of pre-recorded talks on the fundamental concepts. And these were intended to be about 10-minute talks. They're really great background. I highly recommend them. They're going to be a resource which is going to stick around. So feel free to watch those. But what we're looking for right here is this link to the ExoSIMS tutorial. Now, if you missed the ExoVista tutorial on Tuesday, the link to those materials was just above it. And that's going to take you to this GitHub page right here. And it should say D. Safransky Yield Modeling Tool Workshop Tutorial. You're going to scroll down until you get to Easy Way number 1. And it has 2 bullets with links. You're going to click on the first link. And that is going to take you to this Jupyter notebook. It's going to ask you, it's a Google Colab notebook, so it's going to ask you to sign into Google if you've got a Gmail account. And then when you try and run it, it's going to, the way that you run it are these little boxes next to each cell if you're not familiar with a Jupyter notebook, and you can hit play. And it's going to give you this warning, oh no, Google didn't author this. It could be dangerous. No, Dmitry Safransky authored it. It's okay. You can click run. And this first one's going to take a minute or 2. So if you're following along, you want to go ahead and do that to get it out of the way. Now, as I said, this is a really abbreviated version of an hour-long tutorial. So here's what we're going to do. We're actually going to set up a simulation. I'm going to highlight only one thing about what you can do with it, and then we're going to run it, and you're going to actually get to see what the output of it looks like. And then I'm going to do, like, if I've got time at the end, I'm going to do a brief highlight on some post-processing. All right, so that worked, and so we're going to run these sequentially. So next, what it's doing is a pip and soap. ExoSIMS is open source. It's available on GitHub, and it has pip install if that's the way you like to install your Python things. So it's showing you all the dependencies and the modules that it's installing here. I'm going to keep going. It's a lot. Just going to keep going. Now we're going to import our packages, including plotting. And now we're actually going to build a simulation object. So this is what the input file of it looks like. It's a JSON. You can keep these as JSON format scripts, but this is the minimal input. And what you might notice is the names here correspond to those names in the flowchart of the modules that I showed you. And this is the minimum of what you can do. And you'll notice everything is blank. So it's just going to use the prototype modules for this. And so we instantiate that sim object, and it's going to use a whole bunch of defaults and the prototypes. That means there's a lot of defaults that just got used, and we should take a look at what those are. Also, I'll note that we're using the EXEP target list for Habitable Worlds Observatory, which is 164 stars, and we didn't have that many stars that survived the target list filtering. So first we're going to look at the modules, and we can see in the file name here that it's using prototype dot blah 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 module name. It's using prototypes. And some of those, there's an instantiation tree. I'm not going to cover that. All right, so what are the, so let's look at what some of the prototype values are. So here, the default value for the pupil diameter that it's using here is 4 meters, and an integration time upper limit and a wavelength and an inner and outer working angle, which is pretty generous. And then, but what are we using for contrast? ExoSIMS has a few different ways that it can handle contrast. One is you can just give it a number, and it's going to treat that as a flat line in between the inner and outer working angle. You can also give it like the standard format set of PSFs that coronagraph mask designers are supposed to give. It will also ingest those. You can give it a 1D curve, which it will assume is azimuthally averaged. So, but for this demo, we're just using a constant value. I'm going to hit play on the next one. We can also define our science instrument, which really means the camera, the properties of the camera, and if you've got any spectroscopy happening. And now we're going to look at the target list. We only have 134. Where did 30 of the targets go? Well, they probably got filtered out with the binary filter, which is another option. So we're going to turn that off so that we keep all the binary stars. And redo it. And now we've got all of the targets back. Which ones did we miss? We can just take a look at those. All right. Now, there's some other cool stuff that happens, but we don't have time for that. So we're going to scroll down here to item number 5 on the observatory and keep out. And when we get here, instead of just hitting play, because there's some stuff that happened earlier in the notebook, we need to catch that. So I'm going to click inside of here, and I'm going to go up to runtime and say run before. So it'll just run everything that happened before this in the notebook. And now I can run this one. And what we're going to do is we're going to actually look at the orbit that we're using for the observatory. It's running everything before right now. It'll catch up in a moment. There's some good stuff up there about completeness. And completeness is a function of integration time. All right, here we are. And we already ran this. But it's a deep copy of the input specifications, so I'm rerunning it just to make sure we've got it right. And now we can look at the coordinates of the observatory. And our mission's only a year long so that we see all the seasonal variations. And what we're looking at here is the 164 targets. And we're looking at when they're available due to solar keep out. So you got to avoid 40 degrees around the sun. And then you have to avoid 90 degrees away from the sun due to where the radiators are placed, if I were modeling Roman here. So the green is when it's visible and the black is when you're not allowed to look at it. Now we're going to sort this by galactic latitude and make a figure to let us know what the percentage availability is of these different targets. Right? And so, of course, near the sun, where you've only got that plus or minus 40, those are the minimum targets. And then as you get up to higher ecliptic latitudes, you get a better availability on those targets. All right, what does the orbit look like? Hey, it looks like Earth's orbit. That's not very informative. So let's look in the rotating frame as our reference. Oh, there it is. Now it looks like that characteristic kind of potato chip of a halo orbit. And in fact, we are just using the JWST orbit for this. All right, and we can take a look now at what our specification file is. And through the tutorial up to this point that we skipped a lot of, there are some things that we've added. We've added some specific modules, such as the Halo Observatory module. And we've turned off filtering binaries. And, we've changed our solar keep out angles. So this is still a pretty short input file, and it's still using a lot of default parameters, but we can run this. So it's really easy. It's your simulation object.runsim. And now it's making observations. And this is the verbosity that it puts out on the screen if you run them one at a time. So we can see that it made an observation, and here's the star index number, and here's how many planets are around it, and here's how many of them it actually detected. And then it creates an output file that has, it's a list of dictionaries, and each entry is what one observation looks like. So here's all the information that it dumps out for the first observation. It lets you know things about the star and your arrival time and the amount of integration time you took. And it lets you know here for the detection, like here's the amount of detection time that I took, and here's the status. And so this is a vector for each. There were 4 planets around this star, and 3 of them were not within the inner and outer working angle, but 1 was, and it did a successful detection of that. If you're doing characterization, right, which this one has, it went ahead and characterized that planet, and it had a successful characterization of that planet. It also does some false alarm stuff and gives you all this other information about the properties, about your detection system and your characterization system, so that all of that information is, including like where those planets were, their separation angle, and their delta magnitudes. So now you can mine all of that later in the post-processing. And I'm going to switch over now to the post-processing. This is to look back on the GitHub page, and you scroll down to the easy way. This is the second sub-bullet. So what we've done for the purposes of the tutorial is that we have cached, we ran a Monte Carlo of 100 universes, and then we ran that through a post-processing pipeline so that we pull all the information out of it and gather it into a CSV file. And then we've cached that CSV file and made it available here in the tutorial. So now you just have better access to play around with and answer the questions, ask the questions that you're more interested in, like how many planets did I actually characterize? So that is what is here. Yep, this was written by Mike Terman. It's safe. We're going to do a lot of this with pandas, so I'm importing that. And then it's, after it finishes those imports, then we're going to look at some, you can see the heading of some of the CSV file as looking at like, what is the average over this Monte Carlo ensemble of universes of my integration time and detection times and such. And actually on this one, I'm just going to come up to runtime and hit run all so that I can just highlight a couple of things. The first one being, one of the things that you might want to ask is, well, how many detections did I make? Because there's eta sub Earth, so not every star is going to have planets around it. And the first time you look at something, you may not actually see the planets. You're going to do follow-up observations, and then you have to do at least 3 of them spanning more than half a period as a heuristic for, I know this is in the habitable zone. So here's the number of detections, and here's a plot of the distribution of characterizations. And you notice, of course, that we make a lot more detections than we make characterization observations. And so how efficient is that? Well, let's look at the joint distribution of those. That's not very informative, so let's put some contours around it and do a line fit. And we do about 6 detections for every successful characterization. There are other things that you might want to look at, like what are my yields per star and which ones are doing better. And you might want to look at like, well, does that correlate well with the completeness that we calculated when we were filtering the target list? What we can see here is these nearby stars are the high yield stars, and the ones over here on the edge, we get lower yields because they have longer integration times, and it's harder to get a lot of observations on them. And then we can plot things like what is my yield as a function of mission time, or what are the characterizations per month that I do. And that's not good to let you know, like, are you at the point of marginal returns, or do you just need to extend your mission because you're still getting a good slope on that? So that is just a super fast, blazingly fast introduction, not even a tutorial. I don't want you to feel like you can just walk away and pull the trigger and be like, I'm good, I can drive exosyms now. If any of you are really interested in doing that, we are more than happy to provide support and additional one-on-one help to get you up to speed on being able to run exosyms. Are there any questions? Yes. That's a great question. We should always ask that when we're looking at yield results. The language that I use is that a detection as a photometric observation, right? So we were getting everything in the 20% bandpass, and characterization means that we're doing some sort of spectral. So of course I want to specify, and it's easy with just a change of a few parameters in exosyms to say, here's my central wavelength, and here's my bandwidth, and here's my spectral resolution. For this particular example, we were using the water search metric. There's an albedo. So there's not atmosphere types, not yet. It's on our list of things that we would like to add. And exosyms does have the capability to have wavelength dependency of everything, like the QE of the detector and the throughput function and your stellar spectra, but we just haven't added atmospheres, right? The albedo does not have a wavelength dependence at this point. And in the main population that we use, what we had used for the common comparison of HabX and LUVOIR is that gas giants are 0.5 and Earths are 0.2 in albedo. Yes?
A little bit of water. Is it just that you're saying, you're not really worrying about the atmosphere, you're just saying, this is the SNR I need and this vector resolution. That's going to take some amount of time.
Yes.
And you don't have to really worry about detailed stuff of that atmosphere. You're just saying, these are the air bars I need, right?
That's right. And that is also the way that AYO works, so that the people that are experts in spectral retrieval and atmospheres, they do all of their stuff, and they hand us, a parameter which says, okay, to detect water, you need an R of 70 and an SNR of 5. And that's what we set up in the code. And we say our target SNR is 5, and we're going to calculate what integration time we need to get there. And as long as that is under the integration time cutoff, which is a policy, right, that both HabX and LUVOIR adopted 60 days. When you kind of think about how much the planet's likely to move in 60 days, it's kind of sensible. You kind of think about how much observatory time you're assigning, you're allocating to this asset. It's kind of reasonable, but it's also just a parameter in the code that we could change. And as long as it's under that time, then we can go ahead and make the observation. But we have different means of optimization in here. So we do like a benefit cost analysis, and we start with the better deals first and the harder ones later. Any additional questions? Yes?
So if I wanted to change something like the telescope diameter, is it as easy as just reassigning sim.telescope diameter or whatever and rerunning the sim?
Almost.
Okay.
There are a few parameters that also are impacted by the diameter. So depending on how you have inputted your chronograph performance stuff, if you have inputted that in arc seconds, then you need to scale those so it's the correct lambda over D.
Okay.
Right. But otherwise, if you're using like a flat contrast, yes, you can just come up here and say pupil diameter, I'm going to change that. It's going to be 6, it's going to be 20. It's that easy.
Cool. Thanks.
All right, so during the Yield Modeling Tools workshop, all of the talks, including the tutorials, were recorded, and we're in the process of getting those up on the website. So you can watch the longer version of the tutorial, and you can watch the deep dive on exosyms. You can also watch Chris's deep dive for half an hour on AYO. I welcome you to keep an eye on that, and we'll put out an announcement. We'll use Exopag announce for when all those talks are up and available. Thank you. Oops. I've broken the light. Oh, I'm trying to get this stuff out of the way. Oh, I'll see if I can put it on.
Hey, 1, 2. Can you hear me? Okay, how is everyone doing? At lunch, everything is good. I don't know if I can use this. Let's see. No, for this. All right. People online?
The mic is off.
No, it's on. I can hear me. What? I need to turn this way. Okay. Okay, so the goal of this presentation is to talk about sustainability in science. As we look for other worlds, how can we take care of our own planet? And it's going to be interactive. Okay, so the first thing is, what is sustainability? It's the definition that I found online is the ability to be maintained at a certain rate or level. Sustainability, in my mind, should not be limited to just climate, the environment, the limited amount of resources that we have to do things. It should include diversity, inclusion, equity, our well-being, mental health. I invite you to check definition online for what is sustainability. I give a link here for the UCLA webpage, but in this presentation, I don't have time to cover all of those aspects. So I will focus on the carbon footprint, greenhouse gas emission of sustainability, so only that side. But please keep in mind, everything else is also very important. Okay, so the goals of my presentation are simple, I hope. So we are on that quest to discover, beautiful quest, to discover other planets that are habitable or that may have life on them. I think this is a human quest that most of us have somewhere deep inside of us. But I hope that we don't forget a few things. First, there is currently only one habitable planet. It's the one that has chocolate or whatever else you like about this planet. Chances are this is the only one that has it. Even if we detect 25, 100, 1,000 habitable planets, we will not go there and colonize them in the near future. Let's be clear about it. That's not something that's going to happen. For this generation, the next few generations at least, we're not going to just go there and live. So we need to think about this planet first. As far as our people too, sometimes we forget that we are not in a bubble. We don't live outside of the world and we are not belonging to society. But my last point is that we have a deeper understanding of the data, the science behind climate change, because as you've heard during the whole week, we know a lot about climate. We are being listened to. We know that people are coming to talk to us, to look at the beautiful James Webb images or HabWorlds images that we deliver on a regular basis. And quite importantly, we don't have that conflict of interest, perceived conflict of interest that climate scientists may have, because we have no reason to lie, basically. I'm not saying that climate scientists have, but some people may argue that, oh, because it's their science, they may lie about it. Sure. So here are just a few words that I heard over the past few days that show how connected what we do is to climate change. So we heard about ecosystem, greenhouse gas runaway, the fact that finding a planet in the habitable zone does not mean the planet is habitable. We talked about CO2, gas chemistry, recycling, Earth 2.0, pale blue dot. We talked about the oxygen we breathe on Earth that is coming from supernovae and massive stars, water cycle. We want to monitor weather on exoplanets, and I think I heard about Greenpeace, but I'm not sure. Maybe else. Greenpeace, something. Okay, I may not need to cover the facts that the temperature on the planet is increasing. We are reaching 1.5 degree increase since the past century. Almost everything about it is due to our own activities, and it will have dramatic consequences on the climate, and of course consequences on food, biodiversity, and of course it will affect us in very different ways. Of course, some people will be more affected than others. It's usually the same who are affected more than the others. So I could cover all of this, but I thought that maybe just showing you recent news about how New York City was looking like, what, 2 weeks ago, 3 weeks ago? The fact that July 3rd was the Earth hottest day on record until the day after, and the flooding never seen before in the northeast of the US. So, yeah, the present is already telling us what the future may look like. Now, the solution is very simple. It's at least very simple to express. We just need to cut down on our greenhouse gas emission, reduce our carbon footprint by about half in the next few years. Okay, maybe a bit more by the late 2040s, which is when we think HW will launch. So I thought it was very interesting to have those two things in parallel. Okay, so a few more points just to make sure that we're on the same page. Climate change is real, and it's mostly due to our own activities. We do not know what the future will look like. There are many scenarios, and they depend on what we're going to do about it. And we know the solution is simple: to stay on the low, mostly optimistic scenario. We just need to decrease our carbon footprint. Simple to visualize, may not be easy to implement. Okay, so I sent a survey last week, and thank you for a lot of people who answered. I think I have more than 40 answers in the end. It's based on that study from Yale and George Mason University. It's American-centric. It's a study of American people and how they perceive global warming and how they feel about it. And they came up with 6 different Americas: the alarmed, the concerned, the cautious, the disengaged, the doubtful, and the dismissive. And I ask you, what do you think is the distribution, in a way, of the population in the US? By asking you, where do you think most Americans are? And this is what you came up with. Okay? This is what you thought the American population looks like on that diagram. So none of you thought that most Americans were alarmed. Most of you thought they are in the middle, cautious, disengaged, concerned. Okay? And then I ask you another question. I know I may have changed the order of my slide, but anyway. I ask you another question, which was, I think I changed my, okay. I'm going to compare that to what is the real answer first. So the real answer from about 1,000 people, I think, in the survey, but then they keep collecting numbers. So I think I have one official slide. So let's see how close to reality you were. You are not. Okay. So that's a very important point. We have a biased perception of how other people think about climate change. They are way more alarmed or concerned than you think they are. They care more about the planet than you think they are. Okay? Now it shows even more. So I'm going back to your answer to that first question. Now I ask you, where do you position yourself in that diagram? Because you are not like, let's say, average people. You are scientists, you know more, blah, blah, blah. Okay, sure, you may be more educated. For whatever reason, you may be a bit different than the pool of typical people. That's the answer. Okay? This makes me like a bit emotional because it's really nice to see that. I mean, you are all very concerned and alarmed about it. That's great to see. But it shows again that there is a bias, right? Be aware of that. The general population does not feel like this. And there are a few things I would say. So there's a bias between how you perceive the population. There's a bias between how the population thinks and how they should think. Right? 97% of the experts, the climate scientists, tell us climate change is real, it's due to human activity, and we should do something about it. Okay, so be aware of that. And I think my point here when I talk about those bias and this perception and how we feel about climate change is that think about what I said earlier about our expertise in the domain and how we have an opportunity to always share something about, oh, I'm talking about the ecosystem on another planet. What about I say a word about the ecosystem on this planet? I'm talking about CO2 gas cycle and how I can help detect a planet that is habitable light years away. But oh, there is one here that has CO2 and maybe there is something that I can say about it. So use that, the platform that you have on a regular basis when you present talk to insert a message because it will help correct the bias in the general population. Okay, so that was a very long introduction just to set up the context. Now I want to go into what we astronomers can do. But before I do that, I need to make sure that we are on the same page in terms of numbers. So I can't really see the chat online, and I hope the people online will participate. And I have a few questions. Can you guess what the Paris Accord limit, which is the amount of emissions that we are allowed to produce if we want to limit the temperature increase to 1.5 degrees? So they gave us a budget, in a way. They allocate a budget of emissions. What is it when you divide per people and per year? So anyone, sharp numbers, go ahead. And if someone can tell me online, I don't know if people say online, but online, same thing. Just write down numbers. Let's see if you can come up with an answer. Just shout any number.
50.
50. Give numbers.
10.
10.
100.
100.
At least 12.
At least 12. So we have a low limit. I don't know online people if they are giving us anything. No? Okay, so the answer is 2.7. So that's the first reference number. 2.7 tons of carbon per person per year is what we are allowed to emit if we want to keep the temperature increase below 1.5 degrees. Okay, so that's the first number. That's what we want to aim for. Second question, where are we right now? As a human species, averaging the entire world, what is the number? Where are we right now? Go ahead, good.
Around like 25.
25.
200. 200.
200.
More than 2.7.
More than 2.7, yeah. Safe bet, safe bet. I don't know if online we have people. So again, you are very pessimistic, except the more than 2.7. It's only 5. It's only 5, and not so long ago, we were well below that. Okay, so the message here is, 1, we are not too far from what we need to achieve, and 2, not so long ago, we were not too far. So it's a very rapid change. It's something that happened very recently, and so we have hope, I guess, to go back to that level quickly. Okay? But now, of course, the world is not very equitable. So I decided to also show the US national average. So maybe most of us are from this country. I'm not. But this is a mission that is supported by NASA. We are in the US. So let's look at the US national average. So this is my third question. What do you think is the number? So how many tons of carbon equivalent per year per person in the US? The number is from 2016, but it doesn't vary that much from year to year. Go ahead, numbers.
30.
30.
9.
9. 12.
400.
My goodness! Did you get my message? Be a bit more optimistic. Just a little more. 50? Okay. 15 and a half. 15, 16. Okay? 13th worst in the world per person. When you look at the total, we are the second worst, representing 14% of the world total, while we represent something like, what, 5% of the population? China is number 1 in total. I don't remember if they are worse or not per person. There are some very small countries that are very polluting in terms of per capita. As a reference, I should have written those down, but there are a few countries in Europe that are around 5-6 tons. So they are not much above world average, but they are still far from the Paris Accord limit. So keep those numbers in mind. Now, let's look at us. Let's look at our community. Astronomy researchers, mostly astronomers. There have been many papers published in the recent past few years. They've looked at the carbon footprint of our community in terms of attending meetings, and in terms of global scale, like an entire country, what do they emit when they do research? And so, yeah, my next question is, what is a typical professional carbon footprint? Very important point. I'm not talking about whether or not you drive an electric car, whether or not you eat beef, whether or not you go and take a plane to go on vacation 5 times a year. I don't care. professional carbon footprint. What do we emit 8 hours a day, 5 days a week, hopefully not more than that, on average? Any guess? Given now that you have some numbers as references.
2.7.
2.7, okay.
0.5.
Wow, you went from one side to the other, like, big time. Okay.
5.
5? 10?
3.2.
3.2? Okay. So this time you're all very optimistic. So I'm going to give you a few numbers. Published papers, very recent papers. That's the carbon footprint of attending a meeting equivalent to AAS in Europe. So the European Astronomical Society, 1.5 tons of carbon per people attending the meeting. That's already more than half of what we are allowed to do. Okay?
You mean that's the cost just to attend the meeting?
Yep. That's it may have included everything, running the meeting and everything, right? So because that was the last, not the last. I could say a lot about this. It was one of the last in person before the pandemic. Then they said, oh, we're going to do hybrid based on recommendation from their committee that they have formed. And then they decided, well, no, we're not going to do it in hybrid. We're going to go back to in person, even though there is a gigantic carbon footprint for it. Sorry for the parentheses. Okay. But that was attending a meeting. So now let's look at other papers. So I wrote a paper on my previous institute, the Canada-France Hawaii Telescope. So that's a ground-based facility in Hawaii. Close to 17 tons per year per employee. Professional carbon footprint only. There was a paper also so there was a group of papers published in Nature Astronomy in 2020. That was the carbon footprint of the entire Australian astronomical community, 37 tons of carbon per employee. The same number came in that paper from Jürgen Nödelsetter, carbon footprint of infrastructures in the world, astronomical infrastructures, 37 tons of carbon per year per person. They also give tons of carbon per paper, per author and facility. Those are all big numbers. They are like above 10 tons. Like that's not okay. And there are more papers that came out with very large surveys of not only astronomical astronomy field, but across the field, showing the carbon footprint of scientific visibility, showing there is a tight correlation between your footprint and your visibility, which is your H index, the number of publications that you have, very closely related. More than almost 7,000 people responded to that survey in France. And then there's another paper, Concern Yet Polluting. Most people are like you. In our field, most people are alarmed, concerned, very concerned about climate change, and they all agree that we should do something about it. The issue is there. What are the changes that we are ready to implement in our field? What are we ready to do to actually tackle the thing that we all agree we should do? Okay, so I have more numbers, but I'll skip that. So that's my message, please. Our carbon footprint is an order of magnitude at least too large. If we want to meet the challenge of the Paris Accord limit of 2.7 tons of carbon per year per people, we need to decrease our carbon footprint by a factor of 8 and maybe up to 20. And we have a few years to do that. Let's say a decade. And again, it aligns very well with what we are doing in this meeting, trying to prepare for the next mission. So those two things are going to happen at the same time. How are we going to do it? And I have two questions for you. The first one is maybe a bit provocative, but are we supposed to meet the same number? Are we, as a community of scientists, astronomers, are we supposed to aim for the same number as everybody else on the planet? Should we get down to 2.7 tons of carbon per year per person? It's a yes or no question, but I think everybody should ask themselves that question. Do we have the same responsibility as everybody else on the planet, or because X, Y reason, we have the right to pollute more? I know what is my answer. So if you agree with me that yes, we have to meet the same challenge as everybody else on the planet, because we are no different, how do we decrease our carbon footprint by an order of magnitude by the time we launch HW? And so that's my question to you. Let's say in the next few minutes, I don't know what time it is. I have the time up there. Oh, so we have plenty of time. So take a few minutes. Online, do it on Slack, send me a message, whatever you want. I'll read those answers. It's very important. And here, maybe join 2-3 people around you. Decide who among the group will send me an email and come up with 3 ideas. 3 ideas that will decrease our carbon footprint in a significant manner by the time we launched HW. So as we look, as we prepare for habitable worlds outside of this one, how do we maintain habitability of this world? How do we do our part in it? So take a few minutes, and I would ask 2 things. One solution, feel free to go for the easy one. Go ahead, if you have questions.
Yeah, the question was, what are the sources of carbon emission per astronomer?
That's a very good question. That's a very good question. Yes. But if you don't mind, let me just move this, and I will answer that. But that's important to ask that question. So one solution should be an easy one to implement and also easy to convince the rest of the community to implement. But I would like you to think about another one that will be more difficult to tell your peers, please make that effort. But it may lead to a significant decrease in our carbon footprint. Right, those 3 solutions, go ahead and send me an email about it. I'll give you a few minutes, and then I'll give you my concluding remarks. Just to answer your question, a few years ago, when I started to think about this type of problematics, the thing that I was told is the first thing you need to do is assess the carbon footprint of your institute before doing anything else. You need to answer the question that you just asked, basically, where is it coming from? Well, it depends on where you're working and what type of subjects you're working on. It could be computer related, it could be travel related, it could be many different things. Go ahead. Yes? So take a few minutes. I'll conclude at 55. Is that good? Okay. Go ahead. Yeah.
Can I ask a question? Do you know that 37 tons of carbon, is that in those calculations when it's talking about astronomers, does that take into account like the emissions? I know it's like the professional footprint, but does that take into account the footprint of like activities that your research might also produce? Like
So there were 2 papers with 37. One was the Australian community, and it was everything they do in astronomy, and basically their main source was cloud computing cluster of computers. But basically they try, all of those papers, one of the issues that they compare sometimes apples and oranges. So my paper may not have covered all the sources of carbon emission. So there needs to be a plan to have a consistent way to measure our carbon footprint. And there are efforts on that path. In France, they have done that very well. And I'm trying to work on transposing their tool to the US and Chile. So we can compare apples to apples. When you compare, let's say, the carbon footprint of Space Telescope, you can compare it to Noir Lab. You can compare it to any other university in the US. And right now, those numbers, that's why I say, it's a range of 8 to 20, because everybody uses a different methodology. In France, what they have realized is that all the purchases, when you buy laptops, or whatever you buy in institute, actually that has a gigantic carbon footprint. More than travel sometimes, more than cloud computing. So it depends. So for every specific studies, I don't know what they included and what they did not include. I should go back to the papers.
Yeah, thank you.
Okay, it's 55. So let me give you my concluding remarks. And Jason just left. There was a message for him. Okay, so let's think about the facts. So one, our carbon footprint makes research in astronomy unsustainable. We need to realize that we cannot go on like this. Okay? Or we decide that we live in a bubble and we are not entitled to the same responsibility as everybody else on the planet, and we go on like this. But that will backfire. That is my prediction. Of course, our carbon footprint is highly unequitable. People are affected more by it than others. Typically, like in the rest of society, the top 1% are the one who emits the most. But it's a global effort in the end. So we need to understand we are part of the problem. Okay, it's difficult to hear sometimes, but given the answer to the survey that I sent around, you all feel concerned and alarmed, it's good, okay? Because the facts are on your side. The numbers show that, yes, we are part of the problem and we need to fix it. So, as we look for habitable worlds outside of this one, and we try to always build bigger telescopes and look for more data, I would recommend a few things. Use your platform, especially if you work in the field of exoplanets. You are so tightly connected to climate change. Share the information. Just share the word. Convince people that there is no reason for such a bias in how we feel about climate change. Participate at your level in efforts to reduce our carbon footprint, but do it in a significant way. So to answer your question from earlier, look at the carbon footprint of your institute before you start to say, oh, we should switch our electric vehicle, we should switch to electric vehicles. Maybe that's not the main thing we should change. Good, everybody's coming back just for the last few words, perfect. Those are the words that need to be heard. Okay, for HW, what I would love to hear is a commitment from the leadership that we will not do business as usual, that we will actually do better, that we will reduce our carbon footprint, that HW will not be as polluting as its predecessors. So that'd be one, a message, a strong message, but a commitment. And then follow that commitment with action. So I said earlier this week, we should have a carbon footprint system budget. We should measure it, and we should track it, and we should trend it, and we should reduce it. From early on, from now to launch to operation, that should be part of it. And then invest, like support the effort, invest in technologies, methods, culture, change, all of these to significantly make our world more sustainable and our research more sustainable. And I know that maybe my speech was a bit grim, dark, and a bit maybe provocative at some point, but please don't forget, we are capable of amazing things. We send rovers on distant planets. We land on comets. We deploy an origami telescope 1 million of miles away from here. We are more than capable of tackling this issue, as long as we want to do it. So let's be bold. The same way we want to look for extrasolar planets, we should be bold and tackle this problem. Thank you very much. Yeah, that's my mission. Yeah, that's my mission, so you can reach.